I think we're good? Yeah, okay. Okay, great. So I was asked to give a review on where we stand in with gravitational lensing. Can everybody hear me okay? Yeah? All right. So that's essentially what I'm going to do. So gravitational lensing, normally you can classify it into regimes. There's weak lensing and strong lensing. I'm going to talk about weak lensing in particular. Both of them constrain the accelerated expansion of the universe and the nature of dark matter. But most of this talk will be about constraining the growth of structure and the accelerated expansion. We have a couple of surveys that are finishing. They completed data taking and they're processing their final data. So those are KITS, DES, and HSC. And we're already starting the stage 4 surveys. So Rooming Observatory already taking data as well as Euclid. And then hopefully to be launched soon, the Roman Space Telescope. Okay, so that we're all on the same page, what is gravitational lensing? Well, if you have light from a distant galaxy coming to the observer, then light will follow the geodesics of space-time, and then if it encounters some energy density along the way, the path will be distorted from a straight line, which means that in the strong regime, you will see two lens or more lens images of the galaxy, and in the weak regime, you will just see a slight change of shape of this galaxy. In the weak regime, this is what this might look like. You have an overdensity that is, for example, a galaxy cluster, and the shapes of galaxies will be tangentially distorted around the center of this overdensity. So these are all the background galaxies whose light is traveling through or nearby this overdensity. These distortions are very small, so they're roughly percent level, so you need to catch them statistically, which means that you want to have as many galaxies as you can in your survey in order to catch these 1% distortions. This is why we make the compromise of getting photometric redshifts instead of spectroscopic redshifts, because we don't have enough galaxies if we try to get spectra for all of them. Okay, this is the typical patterns that you get, this tangential distortion called E-modes. These ones, these radial patterns can arise due to another phenomenon that I'll discuss in a little bit. And then these B-mode patterns, normally people think of them as an indication that your survey has some systematics due to the masking or PSF being incorrectly modeled or something like that. So every single survey will go and look for these B-mode patterns and say, okay, if I have them, then there's a risk that I'm doing my measurement incorrectly and I need to go correct for it. I would argue that in this era of precision lensing, maybe this is not such a good idea anymore, but okay, we can discuss that in a little bit. Why does lensing constrain cosmology? Well, it's sensitive to this distance ratio between the distance from the observer to the lens and from the observer to the source, which appears here in the prediction of how much convergence, how much lensing distortion you will get in your galaxy. So that probes the distance redshift relation. And then at the same time, the presence of this density that is causing the lensing probes the growth history and the matter distribution. Now, if you want to probe the growth history as a function of time with the hope to constrain the evolution of dark energy, then what you do is you want to bin your data. So you place your galaxies in redshift bins, and then you try to measure the how much lensing you have in this bin, in this bin, in this bin, and also the cross correlations between how much lensing you have in this one and this one, for example, because there's part of the lensing of this galaxy that's coming from the structure here in front of this other one. So they will share some common lensing, and that's why you get the cross correlation as well. Okay. So that's what we would call cosmic shear. It's a correlation of lens shapes with lens shapes. But there are other cross correlations or autocorrelations that we use in this business to try to constrain the cosmological parameters. So now it's very common to perform what we call the 3x2 point correlations, which is not only the cosmic shear, but you add the galaxy-galaxy lensing, so the correlation between galaxy positions and lens shapes. And you also add the galaxy clustering, so positions. Normally, this is not the spectroscopic clustering that we've been talking about throughout this week and past weeks. It usually refers to flux limited or color selected sample that has very good photometric redshifts for which you have a very high number density in your survey. So examples from DES are Red Magic or Maglim for this particular measurement. But you could combine with the spectra. We'll see that that can also happen. All right, so the distance redshift relation lets us probe W of Z. And the hope is that if we have an understanding of what this equation of state, how this equation of state evolves with redshift, then we might be able to map that into different physical theories and then try to figure out what is the origin of this dark energy. And then by adding this sensitivity to the growth history, either from lensing itself or also from adding the clustering, then we're able to probe modifications of gravity. We sometimes do that in a parameterized way through mu and sigma, for example, or specific theories of modified gravity, Horndersky by gravity or non-local gravity. These are, for example, the priorities that we set for ourselves in the context of analyzing the Rubin data, just because we don't have the people power to do every single possible theory. Okay, but all the current constraints are mostly focused on growth. So on this combination of sigma 8 and omega matter. So this is what we currently best constrain from the lensing data. And this is the combination of parameters that we use to assess whether there's any tension with the CMB, because the CMB is telling us what this should be from the high redshift constraints, and then we are getting a value from the low redshift, and then if there's a tension, then something happened in between. So this is the space of surveys that do gravitational lensing. So these are the stage 2 surveys already far in our past, let's say. These are the stage 3 surveys whose cosmological results you're seeing on the archive in the past few years. So KIDS is already pretty much done. DES, the latest results are the year 3 results, but hopefully the year 6 results will come up soon. And then HSC, the latest ones are year 3, but then I think there's one more analysis to come from this. And the stage 4 ones are already starting. So you can see that the area increases as well as the number density. So better CCDs and better telescope technology allows us to probe wider areas faster, so we can also go deeper faster, and that means that we get more galaxies over a larger area. So we're at the level of getting like 100 million galaxies for stage 3. This is a typical number that we would use nowadays to constrain cosmic shear. But now for LSST and Euclid, we're talking, and Roman, we're talking about 1 billion, roughly. Okay, I said we use photometric redshifts, so you can see here the colors representing what filters these surveys observe in order to constrain the photometric redshifts. So most of them observe in UGRI, sometimes UGRIZ. KIDS is a little bit particular because it got an extension to the near infrared thanks to the Viking data. So that's nice because we get 9 bands, and that allows us to get a little bit better redshifts. All right. So now I'm going to give you an overview of where we stand in terms of the stage 3 results of these surveys before we progress to what the challenges are for stage 4. Okay. I'm going to do this mostly through plots from some of the KIDS paper, just because that's the one that I'm involved with. But I'm going to show you all of them, HSC and DES as well. Okay, so the last release of the KIDS cosmic shear analysis is the KIDS legacy. This is the final one. There's no more cosmic shear after this. There will be 3 by 2 points, but cosmic shear, this is it. Okay, takeaway, no tension with Planck. Okay, there's no tension with Planck whatsoever. Why is there no tension if with KIDS 1000 we did have a tension that was, you know, at the level of 3 point something sigma? Well, many things have changed. Main driver has been the increased area and adding a 6 tomographic bin. So just statistics have helped a lot, but there are other things that helped. So in going from here to here, we got better image simulations. Then going from here to here, We did better photo C calibration. And then from here to here, this was just a technique of getting the photo Cs. And then from here to here, it was adding much more, much bigger calibration sample for photometric redshifts. So you can see that only those things drove us from minus 3.75 sigma from Planck to minus 1.6. Then for the legacy analysis, so this is the old KITS 1000, and from the legacy analysis, if you apply the analysis pipeline that we use for legacy in the KITS 1000 data, then this is what you get with 5 bins. If we go from 5 tomographic bins to 6 tomographic bins, so going further in redshift up to redshift 2, then we constrain S8 a little bit better. Now we're at minus 1.4. And then in our fiducial legacy analysis, which is now much bigger because it's 1350 square degrees, now we get a tension that is minus 0.7. So from here to here is just more area, okay? Okay, so no tension with Planck. This is the list of things that we've improved since KITS 1000. And there's nothing in the modeling that has really changed. It's all really statistics and photo C. Yes. Yes. It is a coincidence. You should have been there at the unblinding. It was very interesting. Yes. Okay. Okay, what about results from the other surveys? So here we have Planck in red, so S8 omega matter. Here we have KITS legacy, and then we have DES year 3 and HSC year 3. We're pretty much all consistent. You can see the tension with Planck is very little, up to 2.3 sigma for HSC, but it really depends on how you quantify your posterior and where you put your maximum a little bit. So yeah, it's not really not so much of a tension anymore. Notice that here we have the S8, but here we have this capital sigma 8. So this is just the same thing, but with a slightly different index, just because we're most sensitive to this, to actually this index. But it's okay. Cool. It still constrains the same cosmological parameters. All right, everything's in agreement, so you can think of combining. So this is from Benjamin Stolzner's paper. So again, here we have Planck, and then we have KITS, DS year 3, and then we have the combination of KITS Planck CES, and then if you combine with DESI and supernovae, then this is where we are. So it's like right on top. Okay, so what about opening up the parameter space? So that's a little bit difficult right now. We're not super sensitive yet to W0 WA. That will come in stage 4. But still, I mean, we can try to do this. So this is from the dark energy survey. If you want to open up the parameter space, you really need more probes. So now I'm talking about 3x2 point and not cosmic shear. So these are their constraints from year 3. On W versus omega matter, consistent with -1, but you can see that the error bars are pretty big. This model, if you think about, okay, is this model preferred compared to lambda CDM? The answer is no, and the same thing happens for 3x2 point combinations for the KITS 1000 data. In that case, it was not preferred either, and the constraint was very close to -1. We don't yet have this for the KITS legacy, so stay tuned because more stuff is coming out at some point. So are there still tensions? So we've been talking about the galaxy-galaxy lensing problem, where galaxy-galaxy lensing is low. So Emmanuel showed yesterday some results from KSC, which I'll go back to talk about in a little bit. But the idea is that if you try to measure galaxy-galaxy lensing through the delta sigma profile of this, the matter around the lenses at very small scales, then you get some discrepancy with Planck, right? So Planck here is the pink, And the green are HC lensing measurements, and no, sorry, green is DS plus kits, and orange are HC. And this is low. So why is it that galaxy-galaxy lensing is low at the very small scales? This seems to point to a different problem. So there are possible solutions. So already Emmanuel yesterday talked about the role of baryonic effects in suppressing the power spectrum at small scales.